So yesterday we took a look at exponential functions, and the real characteristic that makes something exponential is it either curves up extremely fast or it starts to go down pretty fast. All right. Logarithm functions are pretty much the opposite. For as fast as exponentials go up, these are much slower, okay, extremely so. So they don't go up fast at all. So we'll take a look at what they look like. Eventually we'll solve some equations with logs, and then we'll do the transformations. So we'll do all the things that we normally do with logs. So first of all, the connection between a log function and an exponential function is they are inverses of each other. What does that mean? It means they have the same connection that like squaring and square rooting have. They cancel each other out. Anytime you graph two functions that are inverses, they are mirror images of each other. But they're not mirror images over the x or the y-axis. They're mirror images over the line y equals x. So I'm going to show you an exponential and a log, and I'm going to show you how to mirror images in a second.
So if we have radical functions, is this like why are logs that are like opposite of exponents not radicals?
So when you have the inverse of something, it has to be something that can cancel it out. So like if you have x to the 1/2 power, right, which means square root of x. The inverse of that would be something that cancels out the square root and gets you back to just having the x. So the function that cancels out square root is square root. So that's why squaring is the inverse of square rooting, because it cancels the square root out. The other way you can see it is if you just type it in on the calculator. Let's type in, I don't know, the square root of 16 and then square it. If when I hit enter, I get the same answer back that I typed in, 16, then I know what I did is an inverse function because it gave me back what I started with. So that shows that it's an inverse function. Did that answer your question?
Yeah, so why are logs the inverse exponentials, not, you know?
So we're going to talk more about that. So there's an equation that we could try to solve. That's an exponential equation. And once I show you how to solve it, it's going to involve a logarithm, and it's going to get rid of this x as an exponent. And you'll see more about it. Okay, so when we start solving them, I think that'll answer your question. And the other reason they are inverse functions of each other is because they look like mirror images. Now, the graph in blue, that's the exponential. The graph in red is the log. But that's not really how the log looks. Okay, so the log, what happens is it starts to get very steep. Whenever it gets steep, the calculator just kind of gives up drawing. So what it really should look like is this. Do this in. This kind of comes down, and that just keeps going down. Now, if you folded that right on the black line, the blue graph would land right on top of the red one, and that means that they are inverses of each other. So visually, that's the reason why they're inverses, because they are mirror images over the line y equals x. Any question on that? Now, when we did exponentials, we had something we got close to as we went further to the left, but we never reached it. What do you call that when you get close to it? Asymptote. It's an asymptote. And what kind of asymptote did we have yesterday? Verticals or horizontals? Horizontals. Right, we had a horizontal. Horizontal asymptote was right there. And as you head further to the left, you get closer to it. Now, logs don't have horizontal asymptotes. This log is basically going to just keep going like this. It's going to go up, but it's going to go up extremely slowly. Very, very slowly. But what kind of asymptotes do you think logs have? Yeah? No, there's no slant, because slant means, yeah, there's no slant. The way we get a slant is with a rational function. Logarithms won't have slants. Yeah, yeah, it's going to be a vertical. So it's basically everything switches between exponentials and logs. The horizontal asymptote becomes a vertical. Even the domain and range switch. Okay? And we'll talk more about that. Okay. Everything switches between logs and exponentials. All right. So as far as visual, that's all we're really going to look at with a visual today for logs. We're going to do more with graphing, but that'll be tomorrow. Okay. So what I have written there, that is how you write a log equation. If you were writing it on lined paper, it would look something like that. The y, the equals, the log, and the x would be right on the line, and the a would be below it. Okay, the a is called the subscript. There are no exponents with what I have on the board right now. There's no exponents there. If I did this, that's an exponent. All right, so that's how you write it, and now how you pronounce it. That's pronounced y equals, or y is, the log, and then since this a is lower than everything, we call that the base. Think of like the base on anything. The base is usually lower. The base is at the bottom. So log base a of x. Okay, so that one would be y equals log base 3 of 5. And what the base does is it just controls like what kind of log you're using. It's kind of like when we do roots. That's a root. That's a root. They're both roots. But the number on the outside controls what kind of root. The one on the left is a cube root. The one on the right is a fourth root. They're similar, but a little bit different. It's kind of the same idea. Well, that's what the base on a log is. On the left, that's a base 5 log. On the right, it's a base 3 log. They're both logs. It's just like they're both roots. There's just a little bit of a different way you have to find it. And then what you're actually taking the log of, that's called the argument. So in the one on the left, the argument is 12. Okay, we're taking the log of 12. And the one on the right, we're taking the log of 5. We're just doing it with different bases. There's 2 special bases that have a name. Okay. If the base on your log is a 10, the name for that is called a common log. And so base 10 is called a common log. It's one of 2 bases that you can do on the calculator just by pressing a single button. And because common log is common, it's used quite a bit, sometimes you don't see the base written. So if you ever have a problem and it just says log x and there is no base, you always assume that the base is a 10. If you want the base to be something other than a 10, then you need to write what the base is. Right? But that is important to remember. that there is a 10 here, but it's like it's invisible. Okay, you don't have to write it when it's a common log. And let me show you where the button is for common log on the calculator. So if you wanted to find the log of 12, the log button is right next to the 7. So you press log, type in 12, and hit enter. And you get 1.079. Let's talk about that number for a second. That 1.079. The answer that you just got right here, that number is an exponent. Anytime you type in log and you hit enter, the number that you get is always an exponent. It's an exponent on the base of that log. So there's no base written here. So what did we say the base is? What is it? 10. Base is 10. Now let's see what happens if we raise 10 to the 1.07918 power. Anyone have a guess what I'm going to get? Yeah, I'm going to get 12. Or I rounded it, so I might get like 11.9, something like that. So 1.07918. Well, if you put in the decimal, it works better. Right, so if you raise 10 to that number, we basically got 12. Right, so that's what a logarithm is. Okay, and that's important. A logarithm is an exponent. That's what it is. So now we know 10 to that power gives you 12. So you could have a question like this: 10 to what power gives you 12? Well, we already know the answer. It's 1.07918. And the way you figure that out is you use a logarithm. So logarithms are used to solve for variables that are in the exponent. That's what they're used for. Any question on that? Yeah.
You go back a slide.
Yeah. So you might have noticed on the calculator, there's two buttons right above and below each other. Log is the top one. There's another one right below it that says LN. 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 That's another special log. And that log has a base of E. Log with a base of E is called the natural log. Now, I told you yesterday, I talked more about what E is. E is just a number in math. It's like pi. Okay. E stands for Euler. It's named after the person that discovered it. His name is spelled E-U-L-E-R, but it's German, so that's why it's pronounced Euler. And the number E is about 2.718. Like pi is 3.14. If you want to find where the number E is on the calculator, it's second, and it's the divided by sign. If you press second and then divided by, you'll get the number E to pop up.
How many digits did E do?
That's actually all I know.
Oh.
It doesn't keep going after that. Like 1828, 1828, you might think it just keeps doing that. It doesn't. I don't remember the next digit, but it's not 1828 again. Okay. We generally don't use the number. We use the E symbol. Okay, so like if I had to take and raise something like E to the 5th power, I wouldn't type in 2.718 to the 5th. I would just type in E to the 5th and get the answer like that.
What is this necessary?
What's that?
What is this necessary for?
What do we use logs for?
Oh, no, the E.
Oh, the E. Other than logarithms, it is used in banking too.
Oh.
If you have, if you want to calculate what's called continuously compounded interest, it's that's the formula for it.
Per.
Yeah, PE to the RT. R is your banking rate, and T is the time. and P is the principal, the amount of money you have in your account. That's the only other formula I know that uses E. I'm sure there's probably a ton of them. That's all I know.
Very specific number.
Yep, it's the number 2.718.
So where does it come from? Because pi comes from it's like a ratio, or well, it's not a ratio because it's irrational, but
Isn't it if you like broke it into triangles? It's the
So if you type in this, I'm not sure it'll completely answer your question, but this is a graph that has something to do with E. If you graph this, 1 plus 1 over x to the x, and think about what happens as x gets bigger and bigger. Well, what happens to 1 divided by x as x gets really big? It gets very small. So this gets very small and gets close to 0 as x gets really big. So then this whole thing would get very close to 1 if this part's getting close to 0. What would this part inside get close to? 1. So as x gets really, really, really big, what's in the parentheses gets extremely close to 1. But does it ever reach 1? No, it just gets close to it. So you're taking a number that's extremely close to 1, and you're raising it to an infinitely large power. Now, if it was 1 to an infinitely large power, it would be what? 1, but it's not 1. It's a little bigger than 1. How much bigger? The smallest amount imaginable bigger. Just barely bigger than 1. So if you graph it, let's hit graph. Do zoom 6. You're going to notice that as you head to the left and to the right, there's a horizontal asymptote. And if you graph E right below it, you'll notice that the horizontal asymptote in that graph is exactly at 2.718.
Oh.
So again, the proof of why that's true, I'm not 100% sure. I'd have to look up why. You can usually use calculus to figure out like an asymptote. My calculus is 20 years old, so it's a little rusty. But that's just an interesting graph that has that asymptote. All right. So that's E. It's the number 2.718. You can also see it in the table.
Is the right part going down infinitely, but we just can't see it because of the calculator?
The right part, yeah. So yeah, it does keep going down. It just gets too steep to see it. But if you go to your table, type in a really big number for x, and then look at what you get for y, 2.718. Okay. So it's the asymptote of that function. And when you have a log with a base of e, you usually don't see it written log base e. You're going to see the abbreviation ln. So instead of writing 5 letters, we write 2. Just an abbreviation.
This is not fully related, just related to the calculator. Is there a way to edit the y column right now?
No, you can only edit the x column because the calculator can't really do algebra.
Yeah.
So to be able to edit the y column, I would have to know how to solve an equation.
Okay.
To edit the x column, it's just doing arithmetic. So not this calculator. Yeah.
is it always lowercase ln or can it capitalize?
No, it's usually lowercase. Sometimes when they print the buttons on the calculator, they use capitals. But once you press it, it always comes up as a lowercase l, lowercase m. Yeah. So ln is a short way of writing log base e. The thing you have to remember, kind of like when you write log without a base, when you write ln, it's hiding the e. Okay, there's a base e that's hidden. Okay, but you got to remember what the base is. So instead of writing this, you're going to see that. And that's the only other base that you can do on the calculator by pressing a single button. Base 10 and base E. Okay, the base E button if I didn't really point out where it was, it's right below the log button, kind of closer to the 4. So if you want the ln of 6, there you go. That's the ln of 6. And that 1.79 number, what is that? It represents,
The exponent.
that represents an exponent. E to the 1.79 power will give you the number 6.
You can just say the natural log of 6, right? Or the common log of 6.
Yeah, the natural log of 6, ln of 6, common log of 6, that'd be base 10.
Alright.
But yeah, you can say that. Okay, other than those two bases, everything else, we just say it's a base 4 log, base 7 log. There's no special name. And I haven't shown you how to do base 4 or any other base besides 10 and E. But I will show you how to do it. Probably Wednesday or Thursday. Okay, let's go back to that picture for a second of the log. So if you remember the domain and the range of an exponential, switch them, and that's going to be the domain and range for logs. Okay, so let's start with the domain.
1, infinity.
It does go to
0.
infinity,
0.
but it goes to 0. Yep. Remember the range for exponentials was 0 to infinity. That's now the domain for logs, 0 to infinity. And what about the range for logs?
All real numbers.
All real numbers. Okay. Logs are going to go down forever, and they're going to go up forever. They're going to go up extremely slow. Okay. Just to give you an idea of how slow they go up, if you go all the way to 100,000 on the x-axis, so you go right 100,000 units, you're only going up 5. Okay, so you go right 100,000 and up 5. Think of how slow that's going. Okay, so domain, 0 to infinity, range, all real numbers. If you do a transformation, will the range ever change?
No.
No. If it goes up and down forever, you can't change the range. But you could change the domain by shifting it left or right. Yep.
Just to check for the infinity symbols, you put a bracket for those, right?
No, you put a parenthesis because you cannot reach them. If you put a bracket, that means you could potentially reach that value, and it's not reachable. Okay, so now what we're going to look at is how can you change from what's called a log equation to an exponential equation. This is a log equation. If I was going to write that same thing as an exponential, it would look like this. And I'm going to show you how I did what I did. Let's start with the log form. So one thing we have to remember with logs is the domain is from 0 to infinity. The log did not go in the negative part of the x-axis. And that's because if you try to take the log of a negative number, it doesn't say you can't do it, but what does it say is happening?
No real answer.
Which means what?
It's imaginary.
It's imaginary. So you can take the log of negatives, but it's imaginary, and we're not dealing with that. Now, that was the log of a negative number. If I try to take the log of 0, it still says I can't do it. But is that the same as the last one? No. That's saying that you can't take the log of 0. You're not allowed to ever take the logarithm of the number 0. And I can tell you why after, but we can't do it. So the domain has to be 0 to infinity, not including 0. So that's why I put greater than 0.
So can you change the mode of a calculator so the calculator would give you an answer? Because it keeps saying like you're in real mode or radian mode. Or...
If I type in the log of a negative, yes I can. I can change the mode on the calculator. Yep. Yeah, it's right under mode. You just press mode, and then you change it to instead of putting it on real, put it on a plus bi. It's the second option.
What's r to e to the 0I?
I think it has something to do with polar, because r usually represents a radius, but I've never used that mode on the calculator. Re to the I theta. Probably having to do with writing complex numbers in polar, which means writing a complex number as using an angle. We're going to do that, but it's not till chapter 9. So that'll be after we finish everything with trig. It's a little ways to go on that. Okay, so this on the left, this is log. In log form, just identify our parts. A is written lower, and what do we call the thing that was lower? The base. X is what you're taking the log of. And does anyone remember what I called that?
The argument.
It's called the argument. And logarithms always equal what kind of number? When you type in log and hit enter, the answer you get represents an exponent. That's your exponent. That's your base. That's your argument. So when we rewrite it, the base stays as the base. The base is always what's written a little bit lower. Logarithm always equals the exponent. That's why y turns into an exponent. And the x, that was the argument. And think about what's eventually going to happen if you argue with somebody every day you see them. Eventually, what happens? Well, assuming you're not violent.
Give up.
You're going to give up, right? You're going to be like, forget it. If you argue with somebody every day, you're going to end up alone, by yourself, on one side. Okay? So base stays as the base. Logarithm always equals the exponent. Argument ends up alone on one side.
Math just got too real.
It got real. All right, so let's see if we can change that to an exponential expression. Okay, so remember what it's going to look like. Base, exponent, something on the other side. We just have to fill those boxes in. Okay, so what's our base?
3.
Base is 3. Logarithm always equals what kind of number? Exponent. So y becomes my exponent. And what ends up by itself? The x, the argument. And that's it. Now you can't solve that because you don't know what y is, but if you knew y was 2, then you could do 3 to the second power and get 9. Okay, but that's all you can do. Any question on that? Let's look at this one. Okay, same direction, change to exponential form. Okay, start with the base. Yep. Yep. Anyone know what the base is? Yeah. Base is 5. Logarithm always equals what kind of number? So that's your exponent. And x is the argument, and that goes by itself. And that's it. Again, nothing you can do with it because you don't know what y is. Okay. Questions on changing to exponential form? Because now we're going to go the other way. Yeah.
So is this when we start to get into like 2 and 3 variable, like separate variable equations? Or?
I don't know. When I have you solve something like this, you'll just have one letter that's missing. This is just practice rearranging it. But yeah, when we get to an equation, you'll see what it's going to look like. There's just going to be one letter in it. Alright, so now let's try it the other way. Change that to a log expression. Well, first thing you have to write down if it's a log expression is the word what? Yeah, you got to write the word log. So put the word log, put your equal sign, and now identify where everything goes. Okay. What's going to be the base on my log?
1.2.
Same as the base on the exponential, 1.2. logarithm always equals what kind of number? Exponent, so that's 3. And the thing that was by itself is your argument. And so you're taking the log of m. And the type of log that you're going to do is a base 1.2. That's it. Any question on that? Yeah.
So if an exponent is just multiplying multiple times, what exactly is a log? Like breaking it down one more.
Not sure what.
Because you can break everything down into addition. Like you can turn multiplication into addition, turn division into multiplication to addition. How do you break a log down into a simpler arithmetic?
So like if you were trying to take something like this and break it down.
Kinda, yeah.
So this really means this. I don't know if that answers your question. It means to take the number 1.2 and multiply it by itself 3 times. That's how you break this logarithm down. You take that number and multiply it by itself that many times. Does that make sense?
Okay, so it's okay. It's just an exponent. Okay.
Yeah, because a 3 is an exponent on the number that's your base. And that's all it just means to multiply the base times itself 3 times. All right, let's try this one. So e to the b equals 9. Okay, start with the word log. What's my base? E, and we'll come back to that in a second. What's the log going to equal? It's going to equal your exponent. Yep. So b. And what's your argument? 9. Now log base e. We had an abbreviation for that. ln. That takes the place of log base e. There you go. So that's ln of 9. And that's something we could type in if they want the decimal. Just type in ln 9. You could write 2.197. You don't have to write 2.197. That's not what it said to do. It just said change it to log form. And that's it. Any question on it? Okay, so let's try to show that what's on the left equals what's on the right. What kind of equation is that? Is that log form or exponential? That's log. So the only thing that I've shown you how to do so far is to change it to exponential. Let's try that and see what happens. Okay, what's your base?
2.
2. Logarithm always equals the exponent. So 3 is the exponent. And what goes on the other side? 8, which is your argument. So now it's just a matter of figuring out, is that true? Well, what's 2 to the 3rd power? 8. So when I simplify the left, I get 8. The right side has an 8 because that's what was right there. And are those equal? Yeah. So log base 2 of 8 equals 3. 2 raised to that power gives you that number. That's what a log is. Any question on that one? All right, so similar kind of equation, except now you're going to be solving for x. Okay, is that log form or exponential form? That's log. Yep. What's my base? 5. My exponent?
X.
Yep, logarithm always equals the exponent, so it's x. And what goes on the right side?
1/25.
1/25. Now, you got to think about that for a second. 5 to a power is going to give you 1/25. Well, what if this was your question? Ignore that. What would be the answer to this one? The one on the right.
X equals 2.
Right, x would be 2. 5 squared equals 25. Now, we don't want to get 25. We want to get 25 flipped. So what kind of number does the exponent have to be?
The reciprocal.
Negative.
Negative. So what do you think the answer would be? Yep. A negative exponent flips the answer. Okay. So keep that in mind. If you're looking for a fraction like that, make the exponent a negative, and then just figure out the number that would give you 25. 2 with a negative. Okay. Any question on that? Yeah?
Make the exponent negative.
If you want to get an answer that's flipped, like a fraction like that.
Okay.
Yeah.
Okay.
So like if you had, I don't know, 2 to what power equals 1/16? Well, I know 2 to the 4th is 16, but I want it flipped. So it would be to the negative 4th. Yeah. Okay, so that's one where the variable is on the right side. Let's look at one where the variable is the argument. Okay, let's see how this one works. Okay, TJ, is that log form or exponential?
Log form.
Yep, that's log form. Landon, what's my base there?
5.
Yep, base is 5. Okay, how about my exponent? Ashley, what's my exponent going to be?
Your exponent is going to be x. No.
Remember, x is the argument. It annoys everybody, so it's got to be all by itself somewhere.
So it is. Why is my brain literally migrating? I have it written right here. Is it just the log? I'm sorry.
So the log is going to
Oh, the
disappear.
1.5.
The 1.5.
Sorry, I was looking at the wrong thing.
So the 1.5 is your exponent. And what ends up on the other side?
Yeah.
X, your argument. Now you just type that in and do it out. 5 to the 1.5 power. If it starts to get too big, that's not going to be that big. But if it gets too big, I would just leave it. 5 to the whatever power. Like if it was 5 to the 30th power, I wouldn't write that out. It's going to be too big.
11.18.
What is it? 11 point?
11.18.
About 11.18. Okay. So any question on solving it where the variable is in the argument? Okay. Let's try one where the variable is in the base.
Would you take the calculated answer where you take 11.18, or would you take 5 to the 1.5 power?
If the directions say round to 2 decimal places, then the 11.18 is fine. If it says write the exact answer, 11.18 is not the exact answer.
So 5.1 or 5 to the 1.5 power?
Yeah.
Okay. Thank you.
Yep. Okay, so we did the base, we did a variable on the right, we did the variable as the argument, now we'll do it as the base. We'll see the variable in every spot. Okay, Jack, what's my base here?
It's x.
Yep, base is x. Darian, what's my exponent?
2.
Yep, exponent's going to be 2. And what goes on the other side by itself? 3. Okay, now how do you get rid of the exponent of 2? You got to square root both sides. So you end up taking that root of both sides. So in this case, it's a square root. Now, normally when you do a square root, how many answers do you get? You get 2. But remember what we said about the argument and the base. It has to be bigger than 0. So you're not going to worry about the negative square root. You're only going to worry about the positive. You have to have a positive answer there. And that's your answer. Square root of 3. Question on that one? Okay. So So the last thing we'll look at are 4 properties of logs, and then we're going to stop there and we'll finish the last thing tomorrow.
We're gonna look at transformations today.
What's that?
We're gonna look at transformations.
No, not today. But the transformations, when we do them, are exactly the same. It's got the A, the B, the C, and the D. And they all do the same thing they always do. Right, so these properties, they're not really, they're more like a special pattern. When you have this pattern, something will cancel out and the answer is automatic. Kind of like this. That's a special pattern. The square and the square root will always cancel, and the answer that you're going to get is whatever you started with. That's basically what these patterns are. So if you have a to the log base a of x, something like this. 5 raised to the log base 5 of 12. The answer that you're going to get is whatever you had right here. Because, bless you, the a and the log a cancel out. They only cancel out because these numbers match. So based on that property, what do you think the answer to my question would be?
Well,
Yeah, the answer is 12. So it's a special pattern where things cancel out. I can't explain why, but for now I'm just more concerned that you know the pattern. If you want to see why, I can show you. Okay. Look at example 1. Pretend like you can't really see what's in the boxes. If you just look at it like this. Would you say that that's log form or exponential form? Yeah, that's an exponential form. Yes, it has a log in the exponent, but it's still exponential form. Base, power, something on the other side. Let's look at this one. Is that log form or exponential form?
log form.
That's log, because if you blocked everything out, base, argument, and something on the other side. Okay, so this is a special pattern where those numbers match. So we could have something like log base 7 of 7 to the 13th power. What do you think the answer to that would be? 13. If these two numbers match, then that part cancels out, and the answer is whatever was what I just pointed to. Now the next formula, I'll show you why that one is true. Think about, before I show it to you, what power can you raise something to so you get back what you started with?
First.
First, everybody agree with that? Anything to the first power gives you itself. Okay. Let's look at this rule. Log base A of A. This is saying that if you take the log and your base and your argument match, the answer is always 1. Let's see why. Okay. Let's change that to exponential form. What's your base there? Which one?
The base, the bottom one.
Yeah, the one in the red box? Okay, so there's your base. A. What's your exponent? 1. Logarithm always equals the exponent. And what's supposed to go on the other side?
The argument.
The argument, which is A in the green box. So all that Rule 3 is saying is if you raise anything to the first power, you get the same thing back. This is how you'd see it in Algebra 1. This is exactly the same rule written as a logarithm. Anything to the first power is 1. Now the last property is another rule. Anything to the 0 power gives you what?
1.
1. Let's think how we would write that as a logarithm. What's your base here? A. What's your exponent?
0.
0. And the 1 is what's all by itself. And what's by itself is called the argument. And that's exactly what that is. A is the base, logarithm equals the exponent, and the argument is what was by itself. So property 4, anything to the 0 power is 1. Any question on the special properties? Fine, so let's try one. So the first thing is try to look at your problem and match it up to one of the properties. So that's 2 to the log base 2 of pi. Which property does that one look like? Yeah?
Number 1.
Yeah, that's the first property. We're just letting a be 2, and we're changing x to pi. All right, so based on property 1, what do you get when you simplify that? Pi. Let's try this one. Log base 0.2 of 0.2 to the negative 4th power. Yeah, which property is that one? That's property 2, where the base and the argument match. 0.2, 0.2. So the answer, what did we just say? Negative 4. Yep. Now, C is a little tricky. My suggestion would be think about ln. What does ln mean?
Log E.
Log
Base E.
base E. So this part right here can turn into that. And then copy down the rest. Now that makes it a little clearer which property it is. Which property is that one now? The 2. It's the same property as the one up above. The base and the argument match. Okay. So what's your answer for that one? Just kt. We don't know what k times t is, but whatever k times t is, that's your answer. Any question on that one? All right, let's do log base 37 of 1. So what do you get if you take the log of 1 with a base of 37? 0. This is saying 37 to what power? It gives you 1. 37 to the 0 power. Let's see. I didn't do 1. Let's do log base 42 of 42. Yeah, this is saying 42 to what power gives you 42? First power. So that's an example of each of those properties. Any questions on that? Okay, so we got through, I'd say maybe like 80% of that. So we'll finish 5.4 part 1 tomorrow. We'll definitely have time because there's only about 15 minutes left. We'll start 5.4 part 2. And then we might start 5.5 and then maybe have half a review day on Thursday. So we'll see. Okay, so let me adjust that. so I erased the last 4 questions, I think. So we just about got through the whole thing. Okay, so 29 to 32. That'll be part of tomorrow's homework. Okay, so 1 through 6, 13 to 16, 21 to 23, and 25 to 27. Bless you.